Hello. Now let's begin our new chapter, Structure of Atom. We initially learned that atoms are indivisible. In fact, atoms are divisible. Atoms contain particles inside them. So let's see what kind of particles are actually present inside an atom. Electrons. Electrons were discovered by J.J. Thomson. Electrons have negligible mass and a unit negative charge on them. Protons. Protons were discovered by E. Goldstein. It has mass almost 2000 times that of electrons and has a unit positive charge, that is opposite to that of electrons. Neutrons. Neutrons was discovered by James Chadwick. Mass of neutrons is nearly equal to that of a proton, and it has no charge, that is, it is electrically neutral. Electron is represented by the symbol E, proton by the symbol P, and neutron by the symbol N. Now let's first see what was Thompson's model of an atom. Thompson's model of an atom was also known as the plum pudding model. It was called the plum pudding model because it resembled the plum pudding. It had a positively charged sphere containing negatively charged species in it. On a whole, the atom was neutral, that means the positive charge equally balanced the negative charged species. This model failed to explain many experimental observations, hence it was discarded. Now let's move on to Rutherford's model of an atom. Rutherford did some experiments and came out with his own model of an atom. His experiment was the alpha scattering experiment. In this experiment, fast-moving alpha particles, that is the positively charged helium ions He2+, were made to fall on a thin gold foil. So now question arises, why in particular he chose the gold foil? He selected a gold foil because he wanted a layer as thin as possible. This gold foil was about 1000 atoms thick, that is very thin in width. Alpha particles are doubly charged helium ion, as I told earlier. Since they have a mass of 4u, the fast-moving alpha particles have a considerable amount of energy. It was expected from the experiments that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, he did not expect to see large deflections. But instead, what happened was, most of the fast-moving alpha particles passed straight through the gold foil. Some of the alpha particles were deflected by the foil by small angles. And surprisingly, 1 out of every 12,000 particles appeared to rebound. As we see in the second figure, these alpha particles, let me change the color. The alpha particles here you can see by this arrow are bombarded on this thin gold foil. What we see is most of them passes through in a straight line without even getting deflected, but some of them get deflected by some angle, and very few, in this figure just one, gets deflected back into the direction in which it came from. Moving forward, let's now see the conclusions of alpha scattering experiment. Point first, most of the space inside the atom is empty because most of the alpha particles pass through the gold foil without getting deflected. Very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. And the third point, a very small fraction of alpha particles were deflected by 180 degrees, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. Rutherford calculated that the radius of nuclei is about 10 raised to the power of 5 times smaller than the radius of atom. Now, features of the Rutherford's model of the atom. There is a positively charged center in an atom called the nucleus. Nearly all mass of an atom resides inside the nucleus. The electrons revolve around the nucleus in well-defined orbits. And third and the last, the size of the nucleus is very small as compared to the size of atom. Even having done all those experiments and suggesting his own model, Rutherford's model was discarded. The reason was electrons revolve around the nucleus in circular orbits. This implies that they would undergo acceleration and hence radiate energy. As a result, they would lose energy and finally fall into the nucleus, making atom highly unstable and matter impossible to exist in the form we know. That is, we have this nucleus here, it's positively charged, and we have electrons surrounding it, moving in specific orbits. Now when this electron radiates energy, it falls towards the nucleus, and hence it makes matter very volatile, that is, it won't be able to exist. The takeaway from Rutherford's model of the atom are: first, you should know what was the experimental setup. Second, you should know what were the observations. Third, you should know the conclusions of the experiment. Fourth, you should know the features of Rutherford's model of atom. And finally, you should know the drawbacks of Rutherford's model of atom. Now moving forward, let's see the Bohr's model of atom. Bohr's model of atom had some postulates. The first was only certain special orbits, known as the discrete orbits, of electrons are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate energy and hence they won't fall into the nucleus and making matter volatile or unstable. This is typically how a Bohr's model of atom looks like. It has a nucleus which is positively charged and it has electrons surrounding it, revolving around it in specific orbits. These electrons do not radiate energy. These orbits are characterized by its orbit number, that is, the first orbit will be n equals to 1, the second orbit will be n equals to 2, and the third orbit will be n equals to 3. Now let's see how these atoms are distributed in different orbits. This model was suggested by Bohr and Bury. The maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number or energy level index, that is 1, 2, 3 and so on. So for n equals to 1, the number of electrons that it can hold is 2 into 1 square equals to 2. For n equal to 2, the number of electrons it can hold is 2 into 2 raised to the power of 2, that is 8. For n equal to 3, it will hold 2 into 3 square, that is 18, and so on. The maximum number of electrons that can be accommodated in the outermost orbit is 8. Electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. That is, first n equal to 1 will be filled, then n equal to 2 will be filled, then n equal to 3 will be filled, and so on. So these were the distribution of electrons in Bohr's model. Now let's look on an important term, valency. Electrons in the outermost shell are known as valence electrons. Valency refers to the number of electrons an atom can lose or gain in order to completely fill its outermost shell. In the case of sodium, the valency is 1, that is, it can lose its outermost electron. The valency of beryllium is 2, that is, it can lose 2 outermost electrons. Valency of carbon is 4, but the case of carbon is different. In case of carbon, losing 4 electrons or gaining 4 electrons is difficult. Hence, what it does is it shares its 4 electrons with other 4 from different elements to complete 8 electrons in outermost shell. Similarly, fluorine has a valency of 1, that is, it can gain 1 electron to complete its octet rather than losing 7 electrons, which is not feasible. Now, let's see some more terms. Atomic number. Atomic number is defined as the total number of protons present in the nucleus. It is denoted by the capital letter Z. For hydrogen, number of protons present is 1, therefore Z equals to 1. For carbon, The number of protons present is 6, hence Z equal to 6, or atomic number of carbon is 6. Mass number. Sum of total number of protons and neutrons present in the nucleus of an atom is termed as mass number. For carbon, let's say mass number is number of protons, that is 6, plus number of neutrons, that is also 6, giving it equal to 12. The case of hydrogen is little bit tricky. What happens in hydrogen is it doesn't have any neutron. Hence, the mass number of hydrogen is simply the number of protons it has, which is equal to 1. Now, how an element is represented? Element is represented by writing its symbol, and on top we write the mass number, and bottom we write the atomic number. For example, if I want to denote nitrogen, how will I denote it? We will write first the nitrogen in symbol form, that is N. The mass number of nitrogen is 14, we will write 14, and the atomic number is 7, we will write 7. Similarly, for carbon, the mass number is 12 and the atomic number is 6. For hydrogen, the mass number is 1 and the atomic number is also 1. Isotopes. Isotopes are defined as the atoms of the same element having same atomic number but different mass number. Hydrogen has 3 isotopes: protium, deuterium and tritium. Protium is 1H1, deuterium is 2H1 and tritium is 3H1. Protium has mass number equal to 1, deuterium has mass number equal to 2 and tritium has mass number equal to 3. But in all of these the atomic number is same, that is 1. In case of carbon, 2 isotopes are present in nature. The first is 14C6 and the second is 12C6. The mass number here is 14 and here is 12, while the atomic number is constant, that is 6. Carbon 14 is used in carbon dating to know the age of fossils. This carbon 14 is radioactive. Isobars. Isobars are defined as atoms of different elements having the same mass number but different atomic numbers. For example, calcium is 40Ca20, while argon is 40Ar18. What we see is both have mass number equal to 40, but they have different atomic numbers. Calcium is 20 and argon is 18. Hence, these are isobars. With this, we end this chapter on structure of atoms. In the next video, we'll start with the new chapter. Thank you.